There's two important capabilities added to ground classification. They are very similar to each other. I first implemented the option to use vegetation index in the ground classification. And more recently, I've added the option of using echo length in ground classification. For a longer time, we have been able to use vegetation index as a direct classification, classifying that anything which has a positive vegetation index goes to a dedicated class. But that is an on-off type of classification. If a vegetation index value is within the limits, then we classify the point. If it's outside the limits, then we don't classify the point. And only vegetation index has an effect on how that point gets classified. What is new in the software is that I can use the vegetation index as a probability factor. So it's not an on-off. It's something where vegetation index affects ground classification, and XYZ is still the one could call the primary information source. So the decision on whether a point is going to be classified is based on XYZ, but affected by vegetation index. And what I decided in implementing this is that ground classification doesn't directly use the color channels. That first there is a step of translating vegetation index into a distance value. So distance is a computed value. So we can call it just value. Very often it's some kind of a distance that we store in the attribute for which the software uses name distance. But distance can also come from vegetation index, and it's a computed value, computed attribute for each point. And the reason to put it to translate the vegetation index into distance is that it gives me the ability to do smoothing. The color information is going to have some noise. And I get a nicer result in the ground classification if I don't use the color information directly. If we instead do some averaging and we smoothen the information. But I don't want to smoothen the color information recorded for the points. That would mess up the what is more of a derived or measured value. So by translating the vegetation index into distance values, I can then manipulate the distance values, modify the distance values with smoothing, and not changing the source information. So the source information stays intact, not modified, and we modify the distance value and will then use distance in the ground classification. So I'm going to read a photogrammetric point cloud. I have X, Y, Z, I have color, and I have class in the point cloud. So we have color and the kind of places where I'm hoping for the vegetation index to give me a nicer result is places like this, where we have dense, short vegetation, and the photogrammetric point cloud gives me points on top of the vegetation, no points in the ground underneath the vegetation, and my ground classification easily climbs to the top of the vegetation when we have a smooth rise of the surface to the top of the vegetation. By just looking at the cross section, it's very difficult to say if this is ground or not. It is the top view from which I, as a human, can understand that it looks like it's shrubs, doesn't look like ground. I have a ground classification macro. And this has been already done up to the point which is vegetation index use. So to speed things up, I have done the first 7 steps in the macro. After the first 7 steps, the points which are potential ground, points which will be considered in the ground classification, are in class 6. And I'll just make in view 2, and in all the views I'll make the line weight bigger so that you can see things a little better. And ground classification has not been done yet. And before ground, I have 2 steps. The first one is compute distance. I have red, green, blue channels in the data. I don't have near infrared. Near infrared would give me the ability to use normalized difference, which is better than visible band difference. But visible band difference already is pretty good in telling us what is vegetation and what is not. And in this step, I have a limit, 0.1. Anything which has a smaller vegetation index value than 0.1 gets a negative distance value. Anything which has a bigger value than 0.1 gets a positive one. And I'm going to run this step. And I'm going to show distance. And we're going to look at a point here which looks green. It gets a small positive value. A point which looks gray gets a negative value. So my gray points tend to be negative. My green points are positive values. But there is some noise in the vegetation index and thereby in the distance. It doesn't look very uniform. So I am better off by using smoothen distance step. So the software for every point takes neighbors within half a meter and averages the distance value. And this results in the distance values changing and being better suited for ground classification. And my last step classifies ground. And now the important thing is to have use distance as rating on. And you can put a weight factor between 0 and 100%. 0, or I think 1 is the smallest that you can put in. 1 is a very small effect. Distance will not affect ground classification result much. And 100% is a big effect. Always the x, y, z of a point is used. So even with the 100%, x, y, z is a key piece of information in deciding if something is ground. The distance only affects how eagerly the software will mold or upwards or follow a point upwards, modifying the surface. And I will run the last step, which is the ground classification using distance as a rating. And now in my views, I can look at what ends up in the ground. None of these hits on the shrubs ended in the ground, and I'm happy about that. And as you can see, the fact that a point is green does not prevent it from becoming ground. So if a point perfectly matches the trend in the surface, it can become ground. But the software is less likely to add a green point into the ground class. We have the similar capability for echo length. And if I would rank the visible band vegetation index, which I just showed, it's a significant improvement. Normalized difference, which requires near infrared, that's better than visible band vegetation index. But echo length is the best. So echo length tells us that the object from which the returned point has been recorded is not a solid surface, that the return pulse is coming from more than just one distance. So it's a very, very good indication telling us that something should not be ground. And echo length, Regal calls this pulse width, and Regal systems is the normal source from which you get the pulse width or echo length information. And the goal is the same. We hope to improve the automatic ground classification result by incorporating echo length into the process. And our steps are very similar to vegetation index. We translate echo length into a distance value. We smoothen distance values, and then we run ground classification using use distance as rating set on. I'll load a small data set in which I have echo length. So these are the attributes that I have in the file. We have amplitude in here. I have renamed what used to be parameter. I've renamed that amplitude because that's the normal information that customers are storing as parameter. Amplitude values stored by Regal as extra bytes for each point. And this is what my data here looks like. And we do have echo length. And the echo length values that we have, there is no fixed definition on what is the unit. It's integer values that come in, but there is no fixed definition on whether the unit is nanosecond or meter or millimeter or something else. So for most data sets, you will have to check how big your values are and adjust the coloring scheme according to the data. And in this case, my echo length values are quite small. The software shows them as if they were meters. That's what TerraScan stores. So if TerraScan computes an echo length value, each integer step is how many millimeters the return pulse is longer or shorter than an expected typical return pulse from a hard surface. Regal has been storing nanoseconds. But the values that we have in this data set are not similar to Regal pulse width values that I have seen earlier, that these are very close to zero. So perhaps these use the same idea that TerraScan uses, that the values are relative values comparing against a typical return from a hard surface, which is nice in the sense that you don't have to know how many nanoseconds the pulse is. What is the typical pulse length, return length? Big values mean that they are longer than expected. Zero means that it's the typical length. So zero means hard surface. Bigger values means it's not a hard surface. And if we'd have negative values, very big negative values would be abnormal returns. But I'm going to open echo length coloring scheme, and show this. Majority of my points have an echo length value which is close to 0, and they show up in gray. Some of the points have a bigger echo length value, and they are now showing up in cyan, green, yellow, or red. Red is the highest value. And you may see that we have some places where there's shrubs. And these places are something of a challenge for ground classification. We have a similar situation as I showed with photogrammetric data. This time it's LiDAR, but the vegetation is so dense that we are not really getting any points that have penetrated to the ground. And ground classification would quite easily climb to the top of the shrubs. Let's take a look at the values that we have. So I want to show echo or see echo length. A gray point has an echo length value of 0, this one. Another gray point has 0, this one has 0.001. So very small values. So all the points which are hits on hard surface mostly have an echo length value close to 0. Some of the points show in color. The yellow point here has an echo length value of 0.034. The red point here has an echo length value of 0.045, indicating that it's not a return from one solid surface, that it's something like vegetation. The return echo is coming from more than just one distance from the scanner. And the position of the point is somewhere between the top of the vegetation and the last point from which the echo or the pulse has reached and come then returned to the scanner. It's the same as vegetation index or color information. Not every point which is vegetation is going to have a very high echo length value. So I have some points here showing up in cyan, showing up in gray, and this one has 0.008, this one 0.03, but that again, smoothing is probably a good idea. So my classification at the moment is that I have default and I have low vegetation. This is the first of many returns and intermediate returns. So it is the default class points which are potential ground from which my ground classification macro is going to use and consider as potential ground. And I have a macro which just the 3 principal steps. First step translates echo length into a distance. And here we have something called neutral length as a setting. What this means is that anything which has 0 as a value in the echo length, that gets 0 as a distance value. And For the ground classification, we are translating echo length values to be to something which is between -1 and +1. Vegetation index values are between -1 and +1. And that's how I've come up with the decision that for the ground classification, the distance values need to be normalized or fixed to be in the range from -1 to +1. Any value from -1 to 0 is considered to be normal probability to be ground. So -1 and 0, they get the same treatment. It's the positive values which are treated as less likely. So a value plus 0.1 is less likely than a value of 0 or a negative value to become ground. And a value of +1 is very unlikely to be ground. And spread defines what translates to +1. So neutral length 0 plus 50 or 50 millimeters, that's going to become +1. And the same on the negative side, 0 minus 50 or minus 50 millimeters would become -1. But in this data set, we don't have any negative echo length values. Everything is positive. So our distance values with these settings are going to be between 0 and +1. I'm going to run that step. And let me see if I've got a distance coloring made ready. Yes. So I get distance values which visually look like this. And as you can see, there's some noise. It's not everything here is gray. And not everything here is red or yellow. And then smoothing, again, is a good idea. I'll run the smoothing step. And now the distance values become more uniform locally. And now I'm ready to do the ground classification. And it's the same principle. Use distance as rating is on. And I step that. This is a small data set, goes fast. And this is my ground classification result. And I get a result in which the shrubs here don't end up in the ground. And it's the same as vegetation index. By incorporating that into the ground classification, we get a result which is better and leaves less manual editing work to be done.